Well, welcome back to our lessons, everyone. This is Mrs. Hanson once again carrying on with our Chapter 1 lessons. This time the focus is on scientific notation from our 6th section in Chapter 1. In scientific notation, a number can be written as Y. The letter Y is just going to be used to designate any digit between a number of 1 and 10. Times 10 raised to an x, and that x is known as an exponent, any positive or negative whole number. Now, the reason we like scientific notation really is a time-saving piece. It's a way to write numbers that contain many leading zeros or trailing zeros. By leading zeros, I mean very, very small numbers, a lot of zeros out front, or a trailing zero is a lot of zeros out at the end of a number. And instead of having to write numbers that are so large with all of these zeros or so small with all of these zeros, we've used a scientific notation, a shortcut, if you will, to represent these values by using a number, let's say like 1, and we go times 10 raised to, let's say, an exponent of a positive 6. This means that I have the number 1 with 6 zeros after it, which we know to be 1 million. 1 times 10 to the 6th is the scientific notation for the standard notation, writing out 1 million with 1 and 6 zeros. So we're learning that standard notation and scientific notation really do represent the exact same numbers. We're just writing them either in a shorthand method or in a longhand method. Healthcare professionals must often deal with very large or very small numbers. For example, blood platelet counts can be 250,000 platelets per mil. Instead of writing all of these zeros out, 1, 2, 3, 4, 5 positions, we will learn that we can write this out by placing one non-zero digit prior to the decimal and then just simply telling you how many zeros come after. How many zeros did we move? How many places did we move to the left? We moved 1, 2, 3, 4, 5 places to place that decimal there. So that very large number can be written as 2.5 times 10 to the 5th. Here we have a hormone, estradiol, found in blood plasma in a very small amount, 0.000000250 grams per mil. So again, you can see that this very small number, it would be quite tedious to write out in standard notation. So we use a technique known as scientific notation. We count how many places we move the decimal. 1, 2, 3, 4, 5, 6, 7 places to get the decimal point. I'm going to add the 0 there. To get the decimal point with one non-zero digit to the left. We moved 1, 2, 3, 4, 5, 6, 7 places to make that tiny number. 2.50 times 10 to the negative 7th would be the scientific notation to represent the grams per mil of this particular hormone. So we write a number, a coefficient, and we go times 10, which is really telling us how many zeros are going to be placed after the whole number. How to convert standard notation to scientific notation. And here's our first example. It says, let's convert these numbers to scientific notation. And the first one is 2,500, 2,500. Remember step 1. We need to move the decimal point to give a number between 1 and 10. Right now, the decimal point is at 20, is right after this 0, 2500. Even though it's not shown, we know that this is the place for the decimal. When we move this to the left, 1, 2, 3 spots, 3 spots places the digit number 2 to the left of the decimal and the rest of the digits to the right of the decimal. How many places did we move? We moved 1, 2, 3 spots to accomplish that task. 2.500 times 10 to the 3rd. Now I'm going to caution you that, remember, this did not have a decimal shown, meaning that these zeros were not significant, meaning that I should not report non-significant zeros in my answer. So keeping the significant figures in mind, 2.5 times 10 to the 3 is correct. And I wanted to explain why we're not carrying these zeros. They are non-significant zeros. So if my standard notation has 2 sig figs, my scientific notation should also have 2 sig figs. How about this number, 0.036? We move the decimal so that it has one non-zero digit to the left, giving us 3.6. We have the times 10, and it's going to be raised to an exponent to tell us how many digits we moved the decimal. We moved it 2 places to the right, meaning that number is very small. We need a negative exponent. We have 2 sig figs in this number. We report 2 sig figs in the scientific notation as well. So remember, this is called standard notation when it's written out in its decimal form. And when we use the times 10 to the, we have what's called scientific notation. Note the number of sig figs in the coefficient must be the same as the significant figures in the original value. And that's what I stressed a moment ago. When I first wrote it, I did it kind of on purpose to just challenge us to think about what would be correct. 2.500 is reporting 4 sig figs, but we're not allowed to do that because this particular number only has 2 sig figs, and so therefore we must match, and we must keep that the same as 2.5 times 10 to the third. When we look at, examples of why we're studying this, for example, here, look at the human body and the number of red blood cells it contains. 2.3 times 10 to the 13 red blood cells. Now, if we had to write that out, 2 times 10 to the 13th, what that tells us is that we have the number 2 and 13 zeros coming after it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 zeros coming there, which when we put our commas in there, it gives us an idea of rather how large this number is. Isn't it much simpler to write 2 times 10 to the 13th power? Positive integers, these numbers up here, if they're positive for the exponent, are very large numbers. Look at here, the diameter of a red blood cell is 0.000006. We've moved the decimal 1, 2, 3, 4, 5, 6 places to get a non-zero digit to the left of the decimal. So 6 times 10 to the negative 6th meters is its scientific notation. Notice that you have a negative exponent. And when you have a negative exponent, those are very small numbers. Why don't we practice? Take a moment and write the recommended daily dietary intake of each nutrient in scientific notation, keeping in mind the proper use of sig figs along the way. I recommend turning off the video, pausing it, coming back when you want to check with me. Alrighty, so here is the decimal point after the 0, and I'm going to move it 3 places to get the first digit that's non-zero to the left of the decimal. I am only allowed 2 sig figs. Notice because there is no decimal point there. And since there's no decimal, these zeros are not significant. And therefore, I have to report my answer with just the same number as the problem provided, so that would be 2 sig figs. So 2.4 times 10 raised to a positive integer, this positive exponent, because this is a large number, and we said that we had moved 3 spaces, 1, 2, 3 spaces to place the decimal after the number 2. 2.4 times 10 to the third. Vitamin B12, all kinds of leading zeros here that are not significant. And so therefore, when we report our answer, we can only have one significant digit, the number 6. I know that this exponent is going to be negative because this is a very tiny number. How many places to move that decimal to get the 6 just to the left of it? 1, 2, 3, 4, 5, 6 times we had to move that decimal place, so that exponent becomes 6 times 10 to the negative 6th grams. How'd you do? Just takes a little practice, doesn't it? And there's our answer, isn't it? 2.4 times 10 to the third, 6 times 10 to the negative 6th. Good work. Here's an additional set of practices. Write each number in scientific notation. Please don't cheat yourself. Try them first and then come back to check. Okay, you've unpaused the video, so let's see how we did. Notice there's no decimal, so these are not significant zeros. So therefore, our answer can only contain 3 sig figs. So it will be 9.32. Now, how many places did we move in order to get that decimal point that's here now? We moved it 1, 2, 3, 4 spots to get that 9 to the left of the decimal. So 9.32 times 10 to the 4th power. 1, 2, 3, 4 spots to the left. It will be a positive integer because it's a large number. Here we have a value of leading 0, so these are not significant. Therefore, our answer can only have 3 sig figs. 7.25 places the decimal with one non-zero digit to the left. Now, count how many times you moved the decimal place. 1, 2, 3, 4, 5. Whoops, I went too far. 1, 2, 3, 4 places the decimal. So this will be negative because it's a tiny number. 7.25 times 10 to the negative 4. Remember, positive integers mean large numbers. Negative exponents there mean that they're smaller numbers. These zeros in number 3 are not significant. Therefore, our answer should contain just 3 sig figs. 6.78 times 10. 6.78 times 10 to the what? Well, let's count. We moved this 1, 2, 3, 4, 5, 6 places to get the decimal so that the number 6 was the only digit to the left. Number 4, all of these leading zeros are not significant. However, at the very end, that is a significant digit because it comes after the decimal point and the non-zero number 3. So I'm going to write 3.0 times 10. Now let's count. How many times did we move the decimal to get the decimal after the number 3? We moved it 1, 2, 3, 4, 5 times. And that will be a negative exponent because it's a very tiny number. All of these zeros are non-significant zeros. Since that's true, they're only there as placeholders. Look, there's no decimal at the end, and that's how I know they're not significant. If I had a decimal there, they would all become significant. That leaves me with 3 sig figs. So 4.52. Now, how many times did we move the decimal to get it to where the 4 is the one and only one non-zero digit to the left? We moved it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 times. That makes our exponent times 10 raised to the negative 12th. And the last one, all of these zeros are leading zeros. They are non-significant, leaving us just 2 sig figs. 2.8 times 10, and I know it will be negative. Now let's count how many. We move the decimal 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 times to get that decimal point between the 2 and the 8. 2.8 times 10 to the negative 11th represents that very small number. And just pausing here because I noticed that I made a mistake, and I'm surprised you're not calling me on the phone saying that. This one up above, 4.52, this was a very large number, not a small number. What was I thinking? Let's talk about that, and I apologize. As I stare here, I'm going, why is that a negative exponent? We move the decimal 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 times, but this is a very large number, so therefore that exponent is indeed a positive number. So there's that correction. 4.52 times 10 to the positive 12. So let me just check. Large number, small number, large number, small number, large number, small number. So those exponents now make sense. And here you can just double check. We have those as our final answers. When we're converting, oops, did I do this one? When we're converting a number in scientific notation to standard notation, remember that if the exponent is positive, the number gets larger. And if the exponent is negative, the number gets smaller. So positive integers are large numbers. Negative are the smaller numbers. 2.80 times 10 raised to the 2 tells us to move the decimal points 2.2 spots to the right to make the number bigger. If I see an exponent raised to the negative 2, I'm going to move the decimal point 2 spots to the left to make the number smaller. Now let's try some of those. Here's a practice that says the average diameter of human hair is about 1.2 times 10 to the 4th meters, and this should be superscript. 1.2 times 10 to the negative 4th meters. Convert this value to a standard number. Well, notice that the negative exponent means that it's going to become a smaller number. So we move the decimal to the left to make the number smaller. Now, to make it 4 times to the left, we go 1, 2, 3, 4. And every time we have this little space in here, that represents a 0. We've moved it 1. Now the decimal is to the left of the number 1. The second time we move it, I need a 0. The third time we move it, I need a 0. The fourth time I move it, I need a 0. And now this is where the decimal has ended up. So I now have a number of 0.00012. And I should start with a non-zero there as well. 0.00012. That is the standard number coming from the scientific value, 1.2 times 10 to the negative 4th. So notice that the negative 4 tells us to move it to the left. And when we do so, that's going to tell us that we moved it 1, 2, 3, 4 places to the left to come up with 0.00012 meters. Try some more. 6.5 times 10 raised to the 3rd. 3.26 times 10 raised to the negative 5th. 3.780 times 10 raised to the negative 2. 1.04 times 10 raised to the positive 8. 2.221 times 10 raised to the positive 6. 4.5 times 10 raised to the negative 10. These are all scientific notation because I have the times 10 indicating the decimal location. I'm asking you to write what's called the standard notation. Just write it as a number with no times 10 to the. And when you're ready, let's come back to check our work. Pause, don't cheat yourself, pause, and then come back. Let's check our answers. 6.5 times 10 raised to the third power in standard form is 6,500. Notice I have 2 significant digits and 2 significant digits reported. Do not put a decimal at the end or the zeros would become significant. 3.26 times 10 raised to the negative fifth means I need to make this number smaller. Remember, the positive said make the number larger. The negative exponent says make the number smaller. 0.0000326 represents the standard form for number 2. Number 3, we made the number smaller by moving the decimal points 2 spots to the left, 0.03780. Number 4, we want to make the number larger, so we move the decimal 8 spots to the right, giving us 104,000,000. 2.221 times 10 to the 6 says make the number larger, and we did so by moving the decimal 6 spots to the right, giving us 2,221,000. And the last one, 4.5 times 10 to the negative 10, we want to make the number smaller, move the decimal 10 spaces to the left, and when we did so, you have 3, 6, 9 zeros, then the number 4, 5, and we've obeyed all of the rules for significant digits. Good work. One little comment quickly about scientific notation on your calculator. If your calculator is all like mine, let's say I want to hit out times 10 to the, you want to find the EE key. In other words, I'm going to hit, let's say, 6.02, and I want to hit times 10. Well, that's the scientific notation button here, EE, and I'll make a value of 23. So as we clear that, notice that it will come out 6.02 times 10, that's what this little E means, to the positive 23rd value. Each calculator is just a little different, but on this calculator, the EE button represents the scientific notation key. One comment is, for instance, do not hit 6.02 times 10, then EE, because that's going to throw you off by a value of 10. Notice that got really big fast. The other thing is don't go 6.02 times, then EE, because that's going to throw you off. You just want to go 6.02 directly EE 23, and notice how your calculator then corresponds to that. So the EE is going to be directly calculating times 10 to the. Don't hit any part of that. So on your calculator, you would hit 4.5 EE negative 10, and it will then read this value. This means literally times 10 to the. Let's apply some problem solving using conversion factors in our next section. Now let's define the term conversion factor, and chemistry is loaded with conversion factors, sometimes called dimensional analysis, if that's a familiar word. And it's simply a factor that converts a quantity from one given quantity into another unit. So converting one unit into another. And we do so by writing out what we call equalities in 2 different forms. For instance, 2.20 pounds is an equivalent value in a kilogram. Of course, this is the base unit here is the metric system, and this is what we call the English system. And so 2.2 pounds is equivalent to saying 1 kilogram. And to use them, we set them up as fractions. So as fractions, we can set up this equivalent value saying 2.20 pounds is the same as 1 kilogram, where I have the pound set over the kilogram. Or I can have the kilogram set over the pound. And in doing so, I just want to make sure that I place the equivalent numbers in the appropriate places. So these again are what we call fractions. And as we decide how to problem solve, we want to consider the appropriate conversion factor to cancel the unit that's given and end up with the desired unit we want. If a number appears in a numerator in one term, that's the top number of the fraction, and the denominator in another term, that's the bottom number in a fraction, then the units will cancel. And the goal, of course, is setting up a problem to make sure all the unwanted units cancel out. So for example, let's say, for example, we want to convert 130 pounds into a kilogram. That's our problem, is to convert pounds to a kilogram. And remember, I don't have to memorize these conversions. I provided you a chart earlier in your note pack that gave you a whole bunch of English to metric conversions. And so this is the conversion equality, and we just saw it on the previous slide, but I know that 1 kilogram is equal to the same thing as saying 2.20 pounds. Notice what unit we are given. We are given the pounds. And what unit do we want to cancel or end with is the kilogram. So step one, what I recommend, right, that's given. What is given in the problem? Well, we're given the number in pounds. So we have 130 lbs is that number that represents pounds. We then need to multiply this by a conversion factor that's going to cancel the pounds and end up with kilograms. So the second step is to write the conversion factor and so in doing so, you want to set it up with the unit that you want over the unit that you are given so that they will cancel each other. Think about that process as what unit do we want? What unit were we given? We were given the unit pounds, and I need to make sure that gets placed on the bottom so that pounds will cancel. What unit do we want? Well, we want to solve for kilograms. So our fraction of want over given places kilograms over pounds. Now go and find those values. 1 goes with the kilogram. Pounds goes with 2.20. And in your next step, you're going to solve, canceling out any units that appear top and bottom. So notice what we've done very specifically. Pounds on the top will cancel with pounds on the bottom, and we've arrived at what we call kilograms. So I have to actually hit that, but the unit we end with is the kilogram. Notice here's the unit we were given. Here's the unit that we want. The conversion factor of want over given cancels those appropriately to convert one into the next. Now on my calculator, 130 times parenthesis 1 divided by 2.20. And my screen reads 59.0909. And let's consider sig figs, right? In the number itself, we were given 2 sig figs from 130. So the 2 sig figs, now remember, the conversion factors don't contribute. The conversion factors don't determine the answer sig figs. It's what was given in the problem. We were given 2 sig figs. So that will determine how many we can answer with. So that final answer in the appropriate number will be 59 kilograms. Just making sure that we see what I've done here on the calculator. I took 130 and I multiplied by parenthesis 1 divided by 2.20 close parenthesis equal. And that's where I got 59.0909 repeating. And then I decided that correct sig figs, 2 of them would be 59 kilograms. And that's our answer there. Notice that the pounds canceled and brought us to 59 kilograms. How many grams of aspirin are contained in 325 milligrams of a tablet? The number and unit given is 325 milligrams. The unit that we want is the gram. So step 1, write the number and unit that's given. So that means I'm going to start my problem by writing 325 milligrams. The next thing I do is write out a conversion factor and when I do so, I want, oh, that's not how you spell that, conversion factor. Think about the unit that you want over the unit that you're given so that your cancellation occurs. So think about want over given. We were given the unit milligram. We want the unit gram. We need to find the equivalency. And you remember what milli means, and we're working to memorize those metric prefix. That stands for thousandth of a gram. You can think of it in either way, and both answers are absolutely perfect. It says 1,000 milligrams is equivalent to the same as saying a gram. That's a true statement. Or you could say that 1 milligram is equivalent as 0.001 grams. That is 1,000th of a gram. So we have choices of how we can place that in. I'm going to share with you what I like to do. I always place the larger unit with the 1. That's just my liking. You can choose either direction, it doesn't matter, but I like to place the 1 with the larger unit so that I don't have these tiny decimals to go with. I know that 1 gram is the same as saying 1,000 milligrams. And when we hit that, notice that milligrams will cancel and the unit we end with is the gram. So on your calculator, we will hit 325 times, parenthesis, 1 divided by 1,000. Close parenthesis, press equal, and we get 0.325. Suppose, just to prove it to ourselves, that we had written our conversion factor by using the want over given, but saying that there is 0.001 grams in a milligram. Instead of having the 1 next to the gram, what if we placed it next to the milligram? And we're going to end up with the exact same answer. Do you see that? 325 times 0.001 still gives us the same answer. We've canceled milligrams and converted to a gram. So I would say, does not matter which direction you use for these metric equivalents, you will find that my preference is to put the 1 next to the larger unit. So there we have it. 1 gram is the same as 1,000 milligrams. We ended up with 0.325 grams of aspirin, canceling the milligrams along the way. If we had 1.65 times 10 to the 9th pounds of polyethylene terephthalate, this is the plastic used in water bottles, and it's the number that's recycled in a year. How many kilograms of PET does this represent? So remember, we're learning 2.2 pounds is the same as a kilogram. Step 1, write the number and unit that you were given. We were given 1.65 times 10 to the 9th pounds. Step 2, set up a conversion factor where you think about what unit do you want over what unit you were given. We were given the unit pounds. We want the unit kilogram. We know that 1 kilogram is the same as saying 2.20 pounds. Our pounds cancel and we have it. So we're going to hit 1.65 EE9. Divided by 2.2. And this number is very large when it comes out. 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7 zeros. $7.5 times 10 raised to the 1, 2, 3, 4, 5, 6, 7, 8 places to get that over. Let me model that if it was a little unsure. 130 pounds. Oops, that's the wrong one. We had 1.65 EE9. See how I'm putting that in directly? That's 1.65 times 10 to the 9th power. Then I hit times 1 divided by 2.2, close parenthesis, equal. We get a very large number. So that's why I wrote that out in scientific notation. 75, again, 2. So here we have 3 sig figs. I need to report 3 sig figs, and then to do so, I have to use scientific notation. Without the decimal, the zeros are not significant. With a decimal, all the zeros become significant. So the only way around reporting just 3 sig figs is to report with scientific notation. 7.50 gives us 3 sig figs. The times 8th power tells us how many zeros are after that final. We've got it. Good work, we've got it. Carry out each of the following conversions, and what I've done for you is kind of help remind you how we're going to set up these conversions. Some of these I would not know without looking up. So I did a little bit of work for us and just found conversion factors from the earlier page in our note pack. All right, so let's go through these. 25 liters to a deciliter. Deci is the 10th of a liter. Start by writing your number and your unit of what was given. We're going to set up a conversion factor, thinking want over given. We were given a liter and we want to go to a deciliter. That came out curly, didn't it? A deciliter. Here we see that 10 deciliters is the same as saying 1 liter. Liters cancel and we come up with a number, and the number will be what we wanted for a DL, a deciliter. So how do we solve that? Remember that you're simply saying 25 times 10 divided by 1. So that gives us 250. And if I place no decimal, that is still 2 sig figs, which we are allowed to report in our answer. Number 2, we have 40.0 ounces. That's our number given. We want to set up a conversion factor, placing the unit we want over the unit we're given. We were given ounces, and we'd like to know grams. So I understand, I had to look this up, that in 1 ounce, there's 23.8 grams. I didn't know that, I had to find it. Ounces cancel, and we are left with the unit gram. So on my calculator, 40 times 23.8. This gives us 952 on my calculator. And we are allowed 3 sig figs because all those decimals are significant, and I reported my answer with 3 sig figs. 3. 32 inches into a centimeter. So this is our given unit, inches. Let's set up a want over given conversion factor to cancel the given unit and bring us out to what we want to know, which is a centimeter. We want inches to cancel, it goes on the bottom. We want a centimeter, therefore it goes on the top. So in every 1 inch, there's 2.54 centimeters. Let's hit that on our calculator. 32 times 2.54. I get 81.28 on my calculator. When I hit 32 times 2.54, I get 81.28 on the calculator. Now, we're only allowed 2 sig figs, so let's fix that. Let's see, the first number we have to drop is a 2, so there's no rounding, so I'll just report that as 81 centimeters. And the last one, we're given 10 centimeters. We want to convert that to a millimeter. On the number line on the metric system, we have 1 centimeter being equivalent to 10 millimeters. Notice the larger unit, centi, gets the number 1. Milli is 1,000th. Centi is a 100th. So they are 1 number spot away on each other's number line. 10 times 10 is 100. And that unit we want is a millimeter. Now let's consider sig figs. How many did we start with? We started with just 1 sig fig. 1 sig fig because that 0 is non-significant, and therefore my number here in the answer is fine. I also have 1 sig fig. So 100 millimeters is our answer. How you doing with their conversions? $40 ounces to 23.8. Did I put that right? 40 ounces. 23.8 grams is 40 ounces. I'm going to hit that again. 40 times 23.8, 952. That's what I have. We're good there. That's not right. 81. Yep, we found that. And then 100. So we're good. I just made a mistake in the answer key there. What if we have more than 1 conversion factor? So we set up a series of steps that are going to kind of start with the unit given and work to what they want. An individual donated a pint of blood, 1 pint of blood. So this looks like what it's given. How many liters of blood does this correspond to? Well, if I go into my chart where I provided you conversion factors, I don't see a pint to liter conversion directly. I just don't see it. But what I do see is a pint to a quart and a quart to a liter. I find those equivalencies. So I see a pathway. Even though it's not a direct pathway, I still see one. I can begin by writing my number and unit of what was given. And what I'll do is set up a first conversion factor that's going to cancel the unit pint and bring me to the unit quart. And I want to do that so I can then cancel the quart and bring me to the liter that I was asked for. Knowing that this is the unit we want, the liter, and this is the unit we were given, I just don't see a direct connection between pints and liters in my standard table. I see a direction I can go. I can go from pint to quart and then from quart to liter. So in 1 quart, we see that there are 2 pints. And in 1.06 quarts, I see that I have 1 liter. Step 1, we canceled pints. Step 2, we canceled quarts, and that liter will be left at the end. Now what about hitting this on your calculator? We start with the number 1, and we're going to multiply by 1/2. Then we'll multiply by 1 over 1.06 and then hit equal. So use your parentheses on your calculator when you're looking at these conversion factors. 1 times parenthesis 1 divided by 2, that's 1/2, times parenthesis 1 divided by 1.06. Don't forget to close those parentheses as your work is showing you. And the calculator reads 0.471698, and it keeps going. Now, how many sig figs are we allowed? Not by the conversion factors, but by the number in the problem, we're allowed 2 sig figs. So the first number we have to drop is the number 1, so we will not be rounding. 0.47 liters is our final answer. Take a moment and pause and just kind of go through those steps so you can see what we've done. We used 2 conversion factors to bring us from pint to liter. Let's carry out each of the following conversion factors as additional practice. So now we're looking at what? Top of page 13? Yeah, that's where we're at. Carry out the following conversions. So notice that I have 2 conversions provided for us. Feet to kilometer. Start your journey by writing out the number and the unit that was given to you in the problem. I want to go from feet to kilometers, but no matter how much I tried, I couldn't find a direct conversion between these two. But I did find a pathway. I found a conversion that would allow me to exchange feet for a mile and then a mile into a kilometer. So I needed both sets of units to achieve what I want from the unit I was given. And so I'm going to get both of these conversion factors set up so I can see the journey I want to take. I want to start with the unit feet and I want to end with the kilometer. So the first unit I was given was the feet, FT. The only exchange I found that was bringing it into a mile. I found that 1 mile was equivalent to saying 5280 feet. I've got the feet to cancel and I'm at the mile. Well, I want mile to then cancel, so it then goes on the bottom of the next conversion, and I want to end with the kilometer, so I place km at the top. And I found this conversion that the same 1 kilometer is equivalent to 0.621 miles. So now let's hit that. Notice miles cancel, and we're at a km, kilometer. 6250 on the calculator times parenthesis 1 divided by 5280, close parenthesis, times parenthesis 1 divided by 0.621, close your parenthesis just as it's written on your screen here, and then hit enter or equal, and we get 1.906 with more numbers after that. Notice we have 3 sig figs because this value is not significant, so I'm allowed to report 3 sig figs only. So let's repair our significant digits. The number that I have here that will be dropped is a 6, so we'll have to round 1.91 kilometers. I'm pausing, let you digest that a moment. We have 3 cups to a liter. The unit that we have is 3 cups, and we want to exchange that into a liter unit. Well, let's try it out. I did not find any relationship directly giving me cups to the liter unit, but I did find a pathway. I found that 4 cups is equivalent to a quart, and I found that 946 mils is equivalent to 1 quart, and that 1,000 mils is a liter. Do you see a pathway? If we start with cups, that's our given unit, I know with certainty that cups has to be on the bottom down here. And if I can get the number of cups to exchange into a quart, I then have the ability to use the second conversion factor. I want quarts to then cancel, and I need to bring it to an ml. And I can see that 1 quart is equivalent to 946 mils. All right, we've got quarts to cancel, and I have the ml and want to bring it to a liter. It takes 1,000 milliliters to exchange into a liter unit. So it was a 3-step conversion factor. First step was to cancel cups and bring it to a quart. Second was to cancel quart and bring it to mil. And the third conversion finally exchanges the mil to a liter. Let's hit that on the calculator. Hit it with me, please. Be my calculator buddy. 3 times, parenthesis, 1/4, times 946 over 1, times 1/1000. And my screen reads 0.7095 liters. We only had 1 sig fig given to us, therefore we can only have 1 sig fig reporting. The second 0 there is not going to be rounded. 0.7 liters is our answer. 1 sig fig. You're getting the hang of this, right? Surely you've done these before. Here I have 4.5 feet to centimeters. Our first conversion, we need to get rid of feet. It goes on the bottom. The only exchange I know is to inches. I don't know directly centimeters to feet. It's not provided for me in the chart, but I did see a pathway. I can see that in 1 foot, I know that there's 12 inches. So that's an equivalency that will cancel feet and bring me to inches. I now see that I have inches on the bottom and centimeters on the top. An equivalent value of a centimeter is 2.54 inches. First step, we canceled feet. Second step, we canceled inches. Always think about what you want over given, what you want over given as you cancel the units. Given a foot, divide by feet. Converting to an inch. Given an inch, divide by inch to convert to the centimeter. And we have 4.5 times 12 over 1 times 2.54 over 1. And my screen reads 137.16. We're allowed 2 sig figs. So that 7 will be the first number that we drop. It needs to round up. So 140, no decimal, and that means we have 2 sig figs, and our final answer would have a unit of centimeters. These just take practice, my friends. Repetition is our friends as we're learning, right? There we have our answer. Sometimes conversion factors don't have to be looked up in a table. They're stated right in the problem. So example and focus at health, what we're looking at is just a couple more opportunities to bring in some healthcare related conversions. If you're prescribed 1.25 grams of amoxicillin, which is available in 250 milligram tablets, how many tablets are needed? This is a very common conversion in a healthcare profession. So notice that we have 1.25 grams is our given quantity that this patient needs. But my conversion here is that in every one tablet, there are 250 milligrams of the active ingredient amoxicillin. So that's our conversion. So we need 1.25 grams of amoxicillin. That means we need a conversion that is going to say milligrams per tablet. This is what we want, and this is the unit that we need to be given. But in order to cancel grams, it needs to exchange to a milligram. So what I first need to do is to get that quantity of gram into the appropriate dose available is 250 milligrams. Remember, milli is 1,000th, so it takes 1,000 milligrams to be the same as a gram. Now what that does is to let me accomplish the cancellation of a milligram and bring me into a tablet. So in every one tablet, there's 250 milligrams. Now look what we've done. We've been able to cancel gram, we've been able to cancel milligram, and we get the number of tablets this patient will need for the prescribed amount of medicine. All right, 1.25 times 1,000 divided by 1 times 1 divided by 250. And I come up with 5 on my calculator. This person will need 5 tablets. And that sig fig, we can consider sig fig, but it makes no sense. You're going to have 5 tablets. That's what you need to give to the patient for their health care. Sometimes they're stated right in the problem. As we've said, we found 5 tablets there. Good work. How about another? A patient is prescribed 0.1 milligram of a drug, and it's available in 25 microgram tablets. How many tablets are needed? So 25 micrograms, remember that a micro is a millionth. And we have 0.1 milligram. So that's our number that is given. Let me just write it out so we can see. Do you remember that milli is 1,000th? That's 10 to the negative 3. And that if a micro is 10 to the negative 6th, right? That's a millionth written in scientific notation. How many decimal points are different between 1,000th with a negative 3 and a millionth with a negative 6? So this milligram needs to be converted into a microgram so that I can consider the tablet dosage. The microgram is the smaller unit. The milligram is the larger unit. I like to place the 1 in front of the larger unit, knowing that 3 zeros separate a negative 6 power and a negative 3 power. It will take 1,000 micrograms, just to remind us what micro means, to be equivalent to a milligram. Let me remind you what milli means, 10 to the negative 3. That's not part of the calculation. I'm just reminding you what those prefix means. So we have 1,000 over 1 as the conversion, and this unit is a micro over milli. All right, so that cancels the milligram. Now, in every 1 tablet, there are 25 micrograms of medicine available. So we have 0.1 times 1,000 over 1 times 1 over 25. That's kind of your key sequence as you calculate that. What's 0.1 times 1,000 divided by 25? And my answer is 4. There are 4 tablets necessary to give this patient the prescribed amount of medicine. Should we try one more together? A dose of 240 milligrams of acetaminophen is prescribed for a 20 kilogram child. How many mils of children's Tylenol with 80 milligrams of acetaminophen per 2.5 mils are needed? All right, so here we have a dose, which is what the prescribed amount, that's our given number, 240 milligrams. That's what this child needs. I want to tell you that the mass of the child is what we refer to as a distractor in math talk. It is not used in the problem. It doesn't matter how heavy or how light the child is. The doctor prescribed 240 milligrams for this child. He probably based it on the mass, but it's not part of figuring out how many volume mils to give them. So, in terms of measuring out the volume of liquid Tylenol, the mass of the child was determined to figure the dosage, but it's not going to help me figure out the volume, so it's not used. So our conversion factor says there's 80 milligrams of acetaminophen per 2.5 mils of liquid. All right, so that's our equivalent of needed to convert. So we have 240 milligrams is what the child needs. I know that 2.5 mils of this medicine will be delivered. Oops, that's the bottom number. My bad. 80 milligrams will be delivered for every 2.5 milliliters of this liquid Tylenol that's measured out. You see how I noticed my error? I knew that milligrams had to cancel, so I know that milligrams has to be on the bottom. So I chose this problem from your homework to just remind you that sometimes problems give you distractor numbers, and here's a great example of that. 240 milligrams is a prescribed dosage, times 2.5 mils divided by the 80 milligrams, and this gives me an answer of 7.5, and that is the volume that I'll have to measure out to give this child 240 milligrams of medicine. That was a one-step conversion factor. Did you get it? That child's mass is a distractor. We measured 7.5 mils of the children's Tylenol. We've been doing a ton of great work practicing in scientific notation and conversion factors. I'm going to stop our lessons here and allow us to kind of process. We have a couple of topics left yet, temperature and density, to wrap up our chapter 1.